I'm Professor Rad, and this is Precalc video 1-9, Increasing, Decreasing, and Constant. In this video, we will be talking about what it means to say that a function is increasing, decreasing, or constant on an open interval. And we'll do an example of identifying the intervals at which the function is increasing, decreasing, or constant. So what I'm going to do is I'm going to step out of the way here, and this is our formal definition for increasing, decreasing, and constant. If you want to take a moment and copy it down, there may be some notation you're not familiar with. Don't worry, we're going to talk about what that notation means. So pause the video, give yourself some space in between each of these things as well, because we'll do some examples that make the definition make more sense. Okay, so hopefully you've copied down this very formal definition, and hopefully you weren't too intimidated by all this notation. So the two notations you may not have seen before are these upside down A's and this like round looking E, C with a nose kind of thing. So this upside down A means for any or for all. So we have that happening in each of these definitions. And then this weird looking E thing means in. So it's these are some set notations for shorthands to say something like we're going to be an increasing function if f of c is less than f of d for all c values that are smaller than d values in the interval a to b. And then similar kind of definitions for decreasing and constant. A function is decreasing if f of c is bigger than f of d for all c less than d in this interval a to b. And we're a constant function if f of c is equal to f of d for all c less than d in this interval from a to b. So this is our formal definition for these concepts. What does that actually mean? What does that look like? Well, think about what it means to be increasing. It means you're going uphill. So an increasing function can look something like this. So you're climbing uphill. You could look something like this. Maybe you have a hill that's not quite, it's super steep to begin with, but then it levels off. Or maybe you have something like this, right, where it's not too bad at the beginning and then it becomes steeper and steeper. So increasing means you're going uphill from left to right. If I want to say, okay, but how does that relate to this formal definition here? Well, let's think about this on a coordinate plane. We'll take this one as our example here. So let's say that this is my x and my y axis. We're going to look at this function. And let's say we're looking at, here's a, and it ends at b. So we're looking on this interval from x being a to b. If you pick any two numbers, c and d, that are in that interval, where c is smaller than d, so here's c, and here's d, then the y value that matches c has to be smaller than the y value that matches d. So this is f of c, that's the y value that matches c, and it has to be smaller than the y value when we get to d. This is because as you move your x value up, in order to be an increasing function, your y values have to be going up. So if I have a bigger x value, it's going to have a bigger y value. That's what this notation is saying. So we have a similar thing going on for decreasing, just flipped. So a decreasing function says, if I have a bigger x value, so if d is bigger than c, I get a smaller y value. F of d is smaller than f of c. So this would be something like going downhill from left to right, or maybe we have something a little bit more smooth, or maybe we have an intense slope that gradually flattens out a little bit. And here we have the same sort of situation going on. So I'll demonstrate again over here. If this is my y-axis and my x-axis, if this is A and this is B, if you pick C and D, picking C smaller than D, then the y value for C has to be bigger than the y value for D. So f of c is bigger than f of d. The y value for c up here is bigger than the y value for d, this one here. So that's what it means to be decreasing on an interval. As you move along the function from left to right, you're going downhill instead of uphill. And a constant function, or a function is constant on an interval, if all the y values are the same for each of those x values. So a constant function is going to look like our constant functions. It's just going to look like a horizontal line. All right, so let's do an example where we look at a function and we try and identify when is it increasing, when is it decreasing, and when is it constant. Alrighty, so for this example, we have the graph of a function over here, beautiful f of x, and we need to identify several things. We have to figure out its domain and its range, and then we want to state the intervals on which it is increasing, decreasing, or constant. And it's very possible it might not have any intervals where it's increasing or constant or decreasing, in which case we would just leave it blank. But I wouldn't do that to you. I'm going to pick an example that does all the things, right? So as you're copying down this function to help you out, here are some specific points. It has a vertical asymptote when x is -6. It goes through the point -4, -2, -3, 0, -2, 2, -1, -1, 0, -4, and 3, -4. And then it kind of does this swoop over here, and it's going to pass through the point 6, -1, as it kind of does its swoop up. All right, so if you wanted to pause this video and copy down this function, and then just as a review, identify its domain and range. And when you've got that figured out, you can unpause, and we'll talk about those features, as well as the increasing, decreasing, and constant. Alrighty, so let's talk about the domain of this function. Remember that the domain is your set of x values that your function is permitted to have. So in this case, nothing happens before -6, and nothing happens at -6 in terms of the function. So I don't have a solid point anywhere here. I know that I'm approaching -6, but I'm never going to reach it based on how the graph has been drawn. So I know that my domain is going to start at -6. And then as I follow the function along, it continues. There are no breaks or anything weird happening. And this arrow on the end here says this is going to continue off and to the right forever. So it's going to go from -6 to infinity. All right, I don't like how that marker is writing, so let's try another marker, see if this one writes better. For the range, remember I'm a giant metal sheet going from bottom to top. So now we're looking at the permissible y values. So this function is kind of interesting because it does have a floor, right? It never goes below -4. And you always want to be careful and check your arrows before you declare -4 to be the smallest. For example, it's entirely possible that I could have drawn this end here with a little loop-de pointing down, in which case that down would be down forever, so it would go to -infinity. But in this case, both of the arrows are pointing up. So I know that this is the lowest it's going to get, that's my floor. Now, it does actually have y values of -4. So instead of using a parentheses, I'm going to use a square bracket of -4. And then as I go up through the function, it never breaks, there's no jumps, it's continuous kind of going up. So we have up towards infinity on either end. We just need one end to say it's going to go off to infinity for the range. So that's our review for identifying the domain and the range of the function. To identify the intervals of increasing, decreasing, and constant, I like to go just from left to right because that's where our orientation, our direction is coming from. As the function goes from left to right, what is happening to the function? Because we are moving from left to right and we're indexing the intervals in terms of x, we're not going to pay attention, or we're not going to record what the particular y values are. We're just going to pay attention to what's going on at those particular x values and at which x value does a change happen. So you can think about this where we're finding intervals of increasing, decreasing, and constant. You can think of that as like finding little mini domains where the direction changes. So when I look at this function, I don't know why I'm an ant, but I always think of myself as an ant walking along this function. So this was a very steep hill at the beginning here towards -6. And as I've been walking from just after -6, really, I've always been going downhill, right? I'm a little ant and I'm walking downhill until I get to this point. And then at this point, the hill starts to go up. So I'm going to look at the x value of this point and the x value where I started infinitely close to. And these are the x values that I'm going to use to indicate my interval of decrease. Because I was going downhill that whole time, I'm decreasing from -6 to -4 between those two x values. So I'm going to start out by saying my decreasing interval, it's going to start at -6 and it goes until -4. After that point, now I'm my ant continuing to walk along this function. And as I walk along the function, I'm going to keep going until I get to the top of the hill. So I'm climbing up a hill here. I change concavity, which just means I went from being scooping up to now scooping down, but that doesn't matter. I'm still climbing up a hill until I get to this point here. So this point happens when x is -2. So I'm climbing up the hill from the point when x was -4 until the point when x was -2. So that means I'm increasing on the interval from -4 until -2. Once I'm at this point, now I'm turning around again, and now I'm going downhill. So I'm going to continue to go downhill, very steeply here. And then I seem to hit a floor here, right? I don't turn around and start increasing again, but the floor levels out and I'm no longer going downhill. So it looks like I was going downhill from here when x was -2 until this point, which happens when x is 0. So I'm decreasing again, and put a union here, from when x is -2 until when x is 0. So starting from here, going to here. Notice that I'm ignoring the y values. I don't care that it stops here when y is -4 or that it started here when y was 2. I don't care. When I'm stating my intervals of increase or decrease or constant, I just care about the x value when it happens. So I'm just recording the x value of -2 up until the x value of 0. Now when I'm at 0, now I'm a flat function and I'm walking on level ground until I get to this point here. So I'm walking on level ground until an x point of 3. So I'm going to be constant on the interval from 0 until 3. And then after 3, now I start climbing uphill again. And I'm going to go uphill until the end of time, which is kind of a bummer. Even more of a bummer, it's getting more and more steep as time goes on. So that's not good for this little ant on his journey here. But oh well. So we're increasing from 3 until forever. So we're going to union on here from 3 until infinity. So that's how we can identify the intervals of increasing, decreasing, and constant. You want to do your indexing by the x values only. You don't include the y values, although the y values do reference when you're going to be turning around or staying flat. So it's helpful, you need to see the y values to be able to make the determination of when it changes. But in terms of recording the information, we only record the x values. Again, think of it as like these little domains. So the increasing domain of this function, for instance, would be from -4 to -2, union 3 to infinity. The other thing I wanted to mention is, and this is different depending on the textbook that you have, is what to do about turning points. So here, for instance, an argument could be made that you were increasing right up until that point, or you were decreasing right after it. So you could make an argument to include a closed bracket at -2 instead of a parentheses. My personal preference and what I'm going on based off of our definitions for increasing, decreasing, and constant is that these things happen on open intervals. So that means you're not doing anything at a turning point. You're turning around. So you're not increasing or decreasing there. You're in the process of turning around. So all of our intervals of increase and decrease and constant are going to be open intervals, meaning they're always going to have those parentheses instead of the square brackets. So I hope you found this video helpful in identifying when a function is increasing, decreasing, or constant. Yeah, and I hope you have a wonderful day, and I'll see you in the next one. Bye for now.